So now we are ready to talk about structured illumination. So if you think about it, I was explaining that Abbe's limit comes from the interference of this highest angle beam in the plus and minus directions, and that gives the highest frequency constituent of the point spread function. However, if you then think about what can we do in a fluorescence microscope, we have also the handle of playing with the illumination. So then you think about, okay, if I interfere a very high angle beam from here and a negative angle beam from here, you will get a very high frequency information pattern, and that you can also use to probe information about your sample. So therefore, maybe we can actually break the Abbe limit in that sense, or we can circumvent it by not just using the emission, but also the excitation. And so this is a very crucial point, that this can only be done for fluorescence microscopy. In Abbe's sense, for transmission light microscopy, no chance, because if you did that, then the amplitude pattern would emerge here in a coherent situation, and putting a second amplitude here would just give you a second amplitude pattern that would independently add to the old amplitude pattern, but it doesn't give you any higher resolution. It just gives you a different direction of resolution. This is very different in fluorescence, where the fact is that the fluorophore does not react as scattering does, linear scattering, to amplitude, but it reacts to intensity. So it's the quantum mechanical process of absorbing a photon and independently emitting a randomly phased new photon. This is really the key to superresolution in the linear superresolution sense. So this is the part of what I call linear superresolution, because the detected light in the end is just a product of illumination, local illumination, and the detection efficiency basically in that pixel. So nevertheless, structured illumination is all about exploiting the fact that you can structure your illumination as well as you can resolve features by detecting them in an imaging setup. So here you are seeing a demo that shows you how structured illumination can be represented as an overlap of very high frequencies with an illumination grating that is periodic. Hello, everybody. So this is a little demonstration of structured illumination. So what you see here in my left hand is a very high frequency pattern. If you're sitting far enough away, you can actually not see the details of this pattern. Because your Abbe resolution of your numerical aperture of the eye is not enough. However, what you see here is another high frequency pattern that is also very, very high frequency. And now the magic happens if I put the two patterns together, like I do here, you suddenly see a clearly low frequency resolved image. And what you also see is when I ever so slightly shift these patterns, you see how the contrast in this image varies, and that can be measured. And so this way, then via structured illumination, you can actually reconstruct the high frequencies. So in a way, you see I'm a little bit cheating, because what we are really interested in is this high frequency information in here, and not the low frequency information that I'm showing here. However, as I say, you can reconstruct that high frequency information with the knowledge of the overlay pattern, the structured illumination that you're putting on your high frequency information in the image. And by the way, in here there's another famous guy. So one task is to actually guess who these two people are. So you see this person and this person. So that's one of the pre-lecture tasks. See you later. So this is summarized in this slide as well. So you see here an object, this little bee that Aurélie just draw with a periodic pattern on it. And in a normal microscope, we would not be able to actually resolve these features, because the microscope, it's beyond the Abbe limit. The microscope would just blur it out. What you see would be like shown here, an equally yellow screen. However, before we image, we have the chance to overlap the fluorophores with an illumination pattern. And if we do so, something funny happens. There comes our illumination pattern. Sorry. So here you see it coming, and the illumination pattern gives you these moire fringes. So there's suddenly some really coarse lines of dark and bright features arising. And now these coarse lines might be below Abbe's frequency limit. And therefore, if we then image now the pattern, the emission pattern arising from structured illumination, you're getting something like this. So the total image would show these structures, the moire fringes. Now, unfortunately, we are not interested in these moire fringes, but we are interested in the original details of what is on the B there. And so the trick is now, because we know that we illuminated with a periodic pattern, we can do a little bit of mathematics and recover the original B pattern, so to say. And how this is done, I'm going to show you in the next slides. Oh, by the way, this moire effect comes from the French term moire, which is referring to very fine fabric, basically. And if it overlaps, it gives you these fringes. And this is a common phenomenon, like you see, for example, here. So these panels here have very fine structures on them. And when they start to overlap, you get these fringes appearing. Interestingly, the wall behind me actually shows a very similar phenomenon. If you have the right camera, you might have seen in previous lectures that I gave that there was a moire pattern in the back. So these are called moire fringes. When I was visiting Bordeaux, like here, I saw a very interesting art installation. So they basically put a very fine grating, like window blinds in front of a window, and then printed some interesting pattern behind it. And when you were passing it, you had this idea that something was moving. It was kind of interesting to watch. So this is what you see in this presentation. Okay, so what is really happening? And now it's interesting that we analyze this whole situation in Fourier space. So you see here that what we really have is an emission intensity. So this is before imaging, but it's just the emitted intensity. And the emitted intensity is described as the local concentration of fluorophores that I put down here as object is a function of x, x being a vector of spatial coordinates, if you want even 3D x, y, z, but at least in x and y. And Ix stands for illumination, or rather excitation intensity as a dependence of spatial coordinates. So it is useful to now look at this very same equation in Fourier space. This might sound like, why would you do that? Because it's quite simple here, and in Fourier space it becomes complicated. However, because imaging itself is easily described in Fourier space, it is worth going through the pain, as you will see. So in Fourier space, it looks like this. We have the Fourier transformed object, and the Fourier transform I indicate by this little tilde on top of the thing. And this gets convolved, and the convolution drawing with a brush operation is written often as an X with a circle around it. Sometimes you find also a star, but in my notation I like to keep this circle as a convolution and the star as a correlation. So in this case it's a convolution of the object Fourier transform with the illumination intensity or excitation intensity Fourier transform. As you see, the units, so these are functions that now depend on k, the spatial frequencies. That's why I wrote of k. And the total gives you the Fourier transform of the emission pattern. So remember this, we have a Fourier transform object convolved with a Fourier transform excitation pattern to yield the emission pattern. But now, of course, this needs to be imaged and go through the optical transfer function. So graphically, we put this equation down here, and you might wonder, what is the Fourier transform of this excitation pattern? Well, in structured illumination, we have a very high frequency pattern that we generate by interfering two laser beams, or rather a split laser beam, and that gives us a very high frequency pattern. And since, like you saw before, it's positive, we have a zero frequency that denominates the constant in the sum of a constant with a sine wave, and the sine wave or cosine wave, whatever you want, is an e to the I kx and e to the minus or I minus kx. So it gives us at plus k and minus k a peak. And since we can phase shift that pattern, moving it left and right, I wrote here sort of in a very crude way, I just wrote down the phase phi 0. So what this really means is e to the I kx plus I phi, if you want, yeah, and minus I phi 0 here. So that means when we shift that pattern, this one sort of rotates in one way in complex plane, and this rotates in the other way. I like to picture things often by putting one spatial frequency coordinate here, but the y direction I reserve for the complex plane. So in the sense that this would be, for example, real part and imaginary part going in the third dimension. So then you can picture yourself things are rotating in the complex plane when you have a phase change. But anyway, this is up to you how you picture it. But now what we are going to do is we're going to sort of, in our head, simulate what's happening in our Moiré imaging setup. So what happens is that we need to convolve the object information, which is something complex. And so I just represent it by some complicated function here. We have to convolve this with 3 delta peaks. But convolving, drawing with the brush, means that you have 3 pencils. So we have to basically add up the signal from the same object being replicated 3 times in Fourier space. So in other words, this is a total mess, right? We have a mess, an overlap of an object with itself copied 2 times around, 1 time shifted to minus k, 1 time shifted to plus k, and then phase shifted in complex plane and overlapping. So what you get is a messy function here that is, well, very tangled, if you want, in some way. And this, remember, was the Fourier transform of the emission pattern. So now it gets imaged by the microscope system. That is now very simple. Imaging with a microscope system means multiply with the optical transfer function. That means that we get something like this. So our measured raw data, apart from the noise, would be this curve. And as I said, you can take not only one image, but several images. For example, 3 images where you phase shift phi 0 in a particular way. And now the nice thing is that phi 0 phase shifts, for example, by rotating the complex plane in the plus direction, whereas this one rotates in the minus direction. So you have 3, and this one doesn't rotate at all. So that means we have 3 independent ways of influencing these, what I call object components. So these pink and yellowish, or orange and pink and gray components, they are all called object components. They're shifted object components. And they are all influenced independently. And that means if we take 3 images, we have in every k position 3 unknowns. What are the 3 values of these things? And if we take 3 measurements, we have 3 knowns, 3 unknowns. We can solve an equation system. And that is precisely what you do in structured illumination reconstruction. So now we have all the ingredients together to reconstruct our images, and I'm going to show you how in the next slide. So we've measured curves like this one, 3 of them. Step 1 in the reconstruction is compensate for the effect of the optical transfer function. So in other words, divide by the optical transfer function. You're going to get something like this. 3 of these. Well, because we have 3 knowns and we have 3 unknowns, you can now apply this equation system. You invert the 3 by 3 matrix that describes the mixing. So this is called unmixing. Having done the unmixing, we have extracted the 3 components. We have them now individual. We have them individually, and we can then, of course, in the next step, put them where they really should be living. And you might see that normally the object in an ordinary wide field image is anchored with its object 0 frequency at the 0 position. But because of the Moiré effect now, stuff has shifted around, and that is a mess, but it's also the beauty of it, because the object component plus 1 is anchored at plus k. That means the 0 frequency lies here, and because our transfer function is still anchored at 0, we can measure all the way to the negative minus k. And now in terms of object frequencies, because of the mixing, the shifting around in Fourier space, we are able to have information that is measured that goes from plus k to the minus k, or rather from 0 to minus 2k in terms of object frequencies. So this way we've measured twice as much information as before. So we shift them into place. The central component stays where it was. That's fine. The plus first component is phase corrected with e to the I minus phi, and then it's overlapped with the first object component. And as you see now, it extends twice out because it stems from here. It was measured all the way to here. So this is really still measured data outside of Abbe's frequency range. So that's why it circumvents Abbe's frequency range here. The same you do with the negative component. You shift it to by plus k such that it zero frequency overlaps, and then you join all three components. So this is actually trickier than I sort of was pretending, and the reason is that the very first step, correct by the optical transfer function, is a bit more problematic than I was showing you. The reason being that you have to imagine there's noise stemming from photon noise that is everywhere, so that gives you sort of a background in all over the spatial frequencies, white noise in Fourier space. And if you have that, now you're dividing by an incredibly small value, let's say 1,000. That means you're multiplying this curve here by 1,000. And that means the noise that is, in this case, much bigger than the signal here, gets multiplied by 1,000. And that would then kill your whole image and get you lots of trouble. And so what you really do is a trick. This is called weighted averaging. So you are saying, okay, when I'm here, why don't I take the pink curve? Because the pink curve stems from the middle where it has a fantastic transfer and the noise is low. So I simply go for the pink curve rather than this corrected gray curve that has an infinitely bad signal to noise here. So the weights differ from spatial frequencies to spatial frequencies. So it's a frequency dependent weighted averaging. The weight would be going all the way to the gray curve here, 50-50 to these two curves here, and all the way to the pink curve here, and from then on it would just be the pink curve. And you might realize, and of course the other way around with the yellow curve here, but you might realize there's a big problem here because the noise would still be infinite at this end of the pink curve, and therefore what you do is you make sure that this curve goes back to 0, and this way you're fine and the noise is killed as well. So you typically do this with a Wiener filtering approach, and so in the end you have a total transfer function that is twice as wide as the original transfer function, and you've measured your object information to double resolution, and that's structured illumination. So the whole thing is summarized in the next few slides for a two-dimensional situation here. So first, again, the simulation, it's a simulated sample here with a few lines. We overlap it with the illumination, gives us something like this. That's the emission pattern before imaging, and then the imaging would blur everything out pretty much. However, in Fourier space, the situation is like this. We have 3 copies of that are overlapping. That's the emission pattern. Then the effect of the microscope cuts out a circular region, which is, of course, the transfer range, the support optical transfer function. So we get something like this. Then we take 3 such images, we disentangle the information, we unmix the information, which allows us to pull apart these 3 object components, shift in frequency space, and blend them back together. And this way we've increased the resolution, but by this animation you also see that we have only gained resolution really in one direction of space, in this case along the x-axis, but not along the y-axis. Our resolution is still limited by Abbe's original frequency in the y direction. So how can we fix that? Well, of course, we just repeat that experiment in a different direction. If you did it now only in y, you would have a problem with the diagonals. That's why typically it is done in 3 different directions, and you get then almost isotropic resolution improvement. So to summarize this, what you see is in a standard wide field microscope where you illuminate the sample homogeneously with just constant intensity, you are limited by Abbe's original frequency limit. Now, because of structured illumination, you get a total transfer function that roughly looks like this, and it has a frequency limit that is twice as high as the original frequency limit. So in a way, we summed the excitation upper limit to the emission or detection upper limit. So now let's go to the practical side of structured illumination. How do you actually set up such a system? Well, you do this by having a laser, coherent light source that does a plain parallel illumination of a diffraction grating. And this diffraction grating gives you three orders: the central diffraction orders, the first and the minus first order. And then in this particular case, you can also block the central order. Then you're left with two orders like I've described. But it turns out that it's quite useful to keep the zero order if you're working with three-dimensional samples, because what you then get, rather than having just a sinusoidal illumination, you get a slightly non-sinusoidal, more like a rectangular illumination if you want. And this illumination has a funny effect that's called the Talbot effect. So you see here a graph that is x, which is this direction, and z, which is the optical axis direction here. And you see that this looks almost like a sinusoidal or distorted sinusoidal grating. However, it then defocuses and refocuses again with a phase shift, and then it defocuses and refocuses again with a phase shift, and so on. So you get this sort of three-dimensional, if you want, lattice of illumination patterns. And this three-dimensional lattice is actually a bit like a wood pile structure. So if you had a pile of woods, put it again onto itself and so on, it looks like this. So this allows you to also gain resolution along the Z direction when you perform the whole thing. The disadvantage is, instead of having to disentangle three components, if you go through the mathematics, you find out that you need to disentangle 5 components, or depending on how you count, even 7 components. And that means you need 5 images for these 5 components. And 1, 2, 3, 4, 5. And once you have them, you can disentangle the 5 components. I'm going to show you experimental data now. So this is the Fourier transform of one of these extracted 5 components. And this is the plus second component. This is the plus first component. This is the extracted 0 component, minus first, minus second component. Now, when you put them all in a picture, I will show you in a second, but you see again, as a reminder, the resolution improvement comes from the fact that you're measuring from the minus edge of the aperture from left side to the other side, which is twice the distance than it would normally be accessible from the center to somewhere. So if you then repeat this in 3 directions, you have all these different components along different directions, and you can then put them together like a puzzle. And it looks like this. And so I've indicated the original abyss border here, and now the new sort of clover leaf shaped looking border frequency, which is almost isotropic and almost twice, well, strictly speaking, can even be a little bit more than twice, because the excitation wavelength is a little bit shorter than the emission wavelength. And yeah, this is all these extra informations. So let's look at the real space pictures that we get. So this is a single picture taken under structured illumination with this 3-beam illumination, giving you 5 components in Fourier space. So this also can be explained by the autocorrelation of the amplitude distribution from the 3 beams, because that's you're measuring intensity, which is absolute square of amplitude, which gives you an autocorrelation in Fourier space. So the 3 peaks from the backfold plane become 5 peaks in the Fourier transform of the illumination here. And you see that even in such a single image, these 5 peaks are well visible. The reason being that a typical object has always the strongest components by far being the 0 frequency. So that's always the strongest thing that there is. And therefore, they also show up directly in the Fourier transform of a single image. And if you have that, we can, like you saw before, disentangle them, piece them all together, and get a high resolution image. So that's the shifted information. There's a big resolution improvement from to here. So this idea was shown in the proof of principle experiments during the time of my PhD. I published this in 1999 in an SPIE proceedings paper. And you see that all the concepts are already there. This is an image of beads that I took, and this is the peaks that you see from the Fourier transform. This is the theory behind it, and this is the reconstructed structured illumination image. You can appreciate the resolution gain. Here you see some fantastic results from the group of Matz, Gustavson, and you can appreciate that these three-dimensional overtime reconstruction that he was able to actually do with his group are showing fantastic level of detail. That is the mitochondria as seen here, together even with their internal crystal-like structures. You can maybe just see these sort of little subdivisions in the mitochondria and how the mitochondria performs fission and fusion. So this is absolutely fantastic data and has been obtained early on in the year 2011. And Matz published already his first paper in 2010 on structured illumination. You can also see some fantastic results from Matz's group, which are shown here. So this is the wide field three-dimensional reconstruction from the year 2008 of a tubulin microskeleton of the cell, the cytoskeleton of the cell. And you see still very high resolution, but it's wide field imaging of these microtubules. And when you go to structured illumination, you get much higher resolution as shown in a second. But look at this. This is the optical transfer function in 3D. So the region of support of the optical transfer function looks like this in 3D. When you then go to structured illumination, you gain fantastic resolution in X and Y and Z. And at the same time, you actually also enlarge your region of support in X, Y, and Z by a factor of 2 in both directions. And you gain optical sectioning like a confocal microscope does. This is again from Matz Gustavson's group, a work by Reto Fiolka, where they imaged multicolor imaging of living cells. And this is the growth cone of an axon. So this is the growth cone here. This is the axon. And you see a cytoplasmic label and the actin and all the dynamics that's happening there. So this is happening all the time, hopefully right now in the brain when you're listening to this talk, by making new connections. So we've, of course, also worked on various aspects on structured illumination. And I want to show you some of the things, which is how to get structured illumination faster. Well, what you see here is a structured illumination setup from the PhD work of Wei-Wen Lu Walter, who did her PhD a couple of years ago here. And you can see how you were seeing here actually how the different structure illuminated this sort of bead pattern here. And how is this done? It can be done quite fast because it's using a spatial light modulator. So the spatial light modulator is illuminated by a laser, and then an excitation filter makes sure that only the right wavelengths comes in there to also prevent any fluorescence from the spatial light modulator here. The quarter wave plate makes the linear polarization that you need for the spatial light modulator into circular polarization, which can then be filtered with a passive Fourier filter. So that was just having holes in it where the right orders go through, so that you get only these orders into the sample that you want to then interfere to get you a perfect sinusoidal grating, and some stray orders because of the pixelation of the SLM are simply blocked here. And then we had an azimuthal polarizer that made sure that the polarization is always azimuthal. So this means that when basically the polarization, when the beams are interfering, is like I point out with the laser pointer here going into the plane of the blackboard here. So, or the paper plane basically. Yeah. So the polarization, the electric field is like this and this, so that it can always perfectly interfere here. But when you're illuminating from the other direction, then of course it would be like this and this, so that when it interferes here, it also perfectly interferes. Otherwise, you have a problem with these very high angle beams. They might not interfere so well anymore if they are sort of electric field vectors point orthogonal, then the interference is gone. One trick that we used to prevent the orientation of the polarization from being messed up is this dichromatic reflectors here and here, which are oriented perpendicular in such a way that what was S polarization and might get delayed by the reflection on the dichromatic reflector then becomes P polarization on the second one. And since they are identical, they basically cancel each other out in their sort of delay, and therefore the polarization is again perfect after these two dichroics. Okay. So here you see one of the results that Wei Wen and Ronnie Förster were able to actually get, which is on the left side you see the wide field data like it would look in an ordinary microscope, and on the right side you see the structural illumination data. And I think there's really no doubt that the resolution is a lot higher. Look at this cluster here and how nicely it is resolved on the right hand side. So one of the more recent advantages, this was where were some things where we thought about how to deal with the current very fast camera technology, which was becoming the bottleneck in our experiments. And this can be done. So these cameras have what is called a rolling shutter. And this is in a way very incompatible with structural illumination, where you always need to acquire whole images at once. And the rolling shutter basically says start integration here, and that it sort of flows downward. And when a pixel reaches the red line, it stops the integration and reads out the data. And so the timing diagrams are shown here. But of course, that's bad because we want to illuminate the whole thing, and that makes it really, really slow, because then we would first have the reset line going through, then integrate, and then the read line, and we are losing lots of time. And so we came up with some strategies of how to illuminate different parts of your image with different patterns at the same time. And you can see this now in the next animation. Well, this is again the effect of the rolling shutter. I can show you how this looks like when you take an image, for example, of a car passing by. It looks like this. So while the read line was still there, nothing much happened. But here the relative speed and angular speed was very fast here when the car passes by, and you see how distorted this wheel has suddenly become here. So this is what I said. This is the animation, how we expose. So you see the start exposure line going through, and at the same time the read line that sort of precedes it directly. And if you just time everything right and you expose the different things like it is shown here, you see that the total camera readout pattern that you obtained is really like here. So it is as if you had acquired fully normal images, but you're losing only 1/3 of the exposure time. So this way we are able to get all the images really, really fast of structured illumination. So you can see the publication here. So now all the 9 images have been acquired. So finally, this led to the current sort of record in speed, which is going at 714 frames per second raw data, meaning about 80 frames per second structured illumination images. And this is the difference, again, between low resolution, high resolution, so wide field and structured illumination images. So can we go even faster? Well, in theory, yes. And there's some neat idea that we worked on, which you see in the next slide. So this is a collaboration with Sarah Abrahamson. And the cool idea is that there's actually ways that you can acquire 3-dimensional stacks, not sequentially by just shifting, refocusing, and imaging again, but you can simultaneously acquire them all in one go. And so with this is some neat hologram that is basically placed here in this Fourier plane. You put a particular hologram, and the different diffraction orders are designed such that they give you different focal planes. So if you're interested in something like this, read this publication. And so it's an idea that also comes from Matz Gustavson and Sarah Abrahamson. And you see that you get like all these 9 orders side by side with different focal planes simultaneously. And of course, all together, we then need to take only our 9 images, for example, and get then a whole stack reconstructed in one go. Actually, you see that the correction optics is fairly complicated, so it's another grating that compensates for this chromatic aberrations together with a prism that is a structured prism plane, and together with the lenses, they form something like this. So to summarize this part on linear resolution improvement and structured illumination, many modes of microscopy exist. Linear methods, linear structured illumination, but also in fact confocal microscopy, if you look at the frequency limit, they yield you a factor of 2 in resolution improvement. However, there's a big difference between structured illumination and confocal microscopy, which is structured illumination has a much bigger transfer function at these high frequencies than a confocal microscope would have. And nonlinear methods, well, that we will have tomorrow. They can get beyond this factor of 2, but they have also sometimes their drawbacks. So with this, I would like to end the lecture of today and just point out that, of course, what you've seen was not my work, but it was mostly the work of Ronnie Förster, Yang Song, Aurélie Hughes, Sarah Abrahams, and many other people, foremost also Kai Wicker, who started basically most of the work in my lab, and many others that contributed to the wonderful images that you have seen. So thanks for listening.